Hi there, my name is Michael. Thank you for tuning into my Workshop 3 presentation, which I will be doing on the push and rotate multi-agent pathfinding algorithm. Um, it was written by these fine folks here listed and published in the Journal of Artificial Intelligence Research. And this happened in 2014. However, the algorithm was written in 2013. A little outline for my presentation here. We'll go over the problem definition and the reason that solving this problem is worth solving and worth optimizing as we continue to improve upon. We'll talk about the push and swap method, which is the algorithm in which push and rotate is actually based on. Um, we will talk about all the different moving parts and pieces to push and rotate that are required really to understand how it works. There's a lot of other moving pieces too, but I tried to keep it to what was necessary to understand. We will also take a look at some of the runtime results as well as result quality. Um, Result quality is referring to how many moves that the algorithm is able to solve the problem in. We will then compare some of the results of the push and rotate algorithm to push and swap. We'll compare it to BuyBox, which is another algorithm that is able to obtain a really good bound for this particular problem. However, it's restricted in a couple of ways that we'll cover. And then we'll do a brief conclusion about the push and rotate algorithm before I let you guys go. To dive right into the problem definition here, I'd like you to consider a simple connected graph, G, VE. Now, a graph is considered simple if there is at most one edge between any two vertices. Um, I'd like you to also consider a set of agents A, where A is less than the number of vertices. So we have to have fewer agents than vertices in order for this to work. Matter of fact, we need push and rotate. It actually requires at least two unoccupied vertices. So we'd actually have at least two less A than V. An assignment function fancy A of agents to vertices. This is their starting location. We have to have a function that defines where they're going to start on the graph. And then we have a goal assignment function, fancy T, of agents to vertices. This is referring to their destination position, where they are trying to get to from their start position. Fancy A and fancy T are considered total, injective, and non-surjective. Total refers to the fact that the location of each of the agents, it has to be specified. Injective refers to the fact that one vertex can only hold a single agent at a time. And non-surjective means that we require there are always more vertices than agents. Like I said earlier, for push and rotate, we require at least two unoccupied vertices. The goal here is to find a sequence pi of moves that transforms the initial assignment to the goal assignment. And we're going to store that in pi, in return pi at the end of the function, or at the end of the algorithm, excuse me. Now, this problem can be defined as an optimization problem, where optimal is referring to a solution consisting of minimal number of moves. So we're trying to do this in as few moves as possible and as fast as we can. Some motivations for improving on pathfinding and optimizing it in general. It's used widely in the field of robotics for just in general making robots move, or even making the hardware on robots move seamlessly. It's used widely in automated guided vehicles, as well as like robots in Amazon warehouses. all moving together across the floor without collisions or minimal mistakes and taking optimal routes. Um, I was first introduced to this problem in general through Unity and game development. I was struggling to understand some of the pathfinding algorithms for enemy AI. It's actually what sparked my interest in this particular algorithm and why I chose to do my presentation on it, is so I could better understand what I was lacking the knowledge of. Um, and another really cool use for these algorithms I was able to, or that was described in the article, was airplane collision avoidance. And I thought that was impactful because, there are lives on the line for this. And so it's imperative that these algorithms work and they work well. Like I said, there are lives on the line. So, but without any further ado, we will jump into the push and swap method, which push and rotate, like I said, is built off of. It was designed by Luna and Burkus around the year 2011. And what it does is it selects agents um, and moves them into their destinations. Um, and its goal is to take the shortest route possible with few restrictions. It's important to note that for our push and rotate, we are going to move them along the shortest path while avoiding agents that are already in their destination. Um, so I'll explain that when we get into the push and rotate itself, but that's one of the differences here between push and swap. But push and swap is really defined by what it does when it encounters other agents. There's a priority status here between the agents. So in the priority refers to the order in which we're moving them. If the blocking agent has a lower priority than the moving agent, it'll try to push it along the path, which contains no higher priority agents. Obviously, you wouldn't be able to push a lower priority agent past a higher priority agent. But the goal is to get it into an empty vertice to get it out of the way so that it can get to its destination. If the blocking agent has a higher priority than the algorithm, then the algorithm will instead attempt to exchange their positions using the swap operation, which I'll explain in a moment. Um, the higher priority agent must be returned to its destination so that the resolve operation is used to attain that. So if we move an agent that's already in its destination using the swap operation, it's imperative that it makes its way back to its original spot um, in order for this to be solvable. Um, So some shortcomings for this particular algorithm include the fact that it doesn't identify polygon graphs, graphs containing a single cycle. Um, this is an example here of a polygon graph. Where's my mouse? There it is. This is a polygon graph here. So the reason it's imperative that we know if it's a polygon graph or not is because the swap operation actually will not work. It will fail if there isn't a vertex of degree 3 or higher. Polygons obviously only have vertices of degree 2 or higher. And the push and swap method is not complete by any means. The clear operation is used to swap, is used in swap, and it's to empty the neighboring vertices of a junction to make room for the swap. Now I'll go to the next slide to show you, but this is the operation I'm talking about here. So our goal is to get A2 to where A1 is. So in order to do that, we have to move A2 out of the way, move past A2, and allow A2 to move past us. Now we have effectively swapped. Without that third vertice, this would be impossible. So another shortcoming here is that recursive calls are possible after the swap operation. and recursive calls here could result in higher priority agent being 2 steps removed from its destination, and this could cause a failure. Um, this in this figure, it doesn't matter who is moving. Um, like both A and A1 and A2 are trying to get where each other are. Um, one is blocking the other, and uh, this is along their shortest path. So a swap is attempted, but there are no vertices in this graph with degree 3 or higher, so it would fail. Um, all of these shortcomings that are listed here are resolved in the push and rotate algorithm by first having agents look for the shortest path without any finished agents, like I said, instead of just the shortest path. Um, Second, they have updated the clear function and made it so that um, it makes no recursive calls and it returns everything the way it's supposed to. Um, they have changed the way that an agent is returned after the swap, which makes use of a new operation called rotate, which I will also explain here shortly. Um, and excuse me, and to account for the isthmus um, issue, in an isthmus is essentially a shape similar to this, where we have issues with the swap operation. Essentially, is what it's describing. But the new algorithm rotate, um, uh, or I'm sorry, in push and rotate, they develop new algorithms to decompose the problem into subgraphs, um, which I'll explain here shortly. But um, it also assigns these agents to the subgraphs and then determines the agent priorities based on the relation of the subgraphs. And that's the just on how push and rotate works. There are a couple of phases, obviously. We have a couple of phases to our pre-processing, and then we have a lot of different things that happen in our moving agents to their destinations phase. But starting with pre-processing, what we're going to do is we're going to divide those subgraphs, assign agents to them, and then based on the subgraph priorities, we'll determine agent priorities. And then for the moving agents to their destination portion, we have to determine the agent's shortest path, excuse me, attempt to move it along this path, um, and then determine what to do if other agents are encountered during this path. Basically, the gist of it is that lower priorities are we're going to try to push, and then higher priorities we have to swap. Um, and lastly, we're going to do our best to prevent recursive calls using some heuristics and post processing algorithms. I'll get into that a little bit too. So this first portion here, this constructing the subgraphs. Um, oh, I'm sorry. I also wanted to explain that the priorities a little bit. So lower priority refers to what hasn't been planned yet. Um, and higher priority has been planned for and it already occupies its destination. So uh, it, it, if it's a higher priority agent that we're engaging, we need to move both agents to a vertex of degree 3 or greater. And then we have to clear the two neighbors in order to perform that exchange operation. Um, and after the exchange operation is finished, we're going to reverse the moves apart from the actual swapping the agents if there are any other vertices involved. We just want to make sure that we're only moving the two that we're trying to uh, exchange. And we have to replace or we have to reverse the moves made in order to clear up space to make these moves. That's essentially um, what's going on. And it's imperative that the higher priority agents return to their destination if they have been manipulated in order to in a swap operation, for example. Um, and that's one of the reasons that there were recursive calls in push and swap. And the rotate operation is what actually accounts for that not happening. Now we can get into constructing our subgraphs. Um, Definition one states biconnected components. Let G equal VE be a simple connected graph. Two edges, E1, E2, are elements of E. They are equivalent if and only if E1 is equal to E2, or there is a cycle in G containing E1 and E2. This is an equivalence relation. The equivalence classes together with incident vertices are the biconnected components of G. So we can see here that there are 10 biconnected components and vertices S1 through S5 with degree 3 that join the biconnected components. So these are the points that uh, connect our non-trivial parts of the graph. Um, Definition 2, I believe is the next one, maybe not, no. So definition 2 states that these subgraphs are a subset of the vertices, obviously. And we split them up in a way like this. So first, we find all the non-trivial biconnected components. If we removed a vertex, the graph would separate, which is like the opposite of biconnected. So, like biconnected graphs, they all have vertices of a degree high enough where we won't break it apart into multiple graphs if we removed a single vertice. So what we're going to do is we're going to add all the vertices of degree 3 or higher that aren't part of a non-trivial biconnected component to the set S. Now our while loop here, all of the elements of S that have vertices with distance less than or equal to the number of empty vertices minus 2, they're joined into one subgraph. So I know that's a little difficult to understand. This is where I struggle the most with understanding how this algorithm works. But this vertex here would be assigned to S1 because its distance is less than or equal to the number of empty vertices minus 2. So it is within range to be part of S1. It's important to note that the components are connected by isthmus. And like I said earlier, that word is kind of weird, but they're all connected by these little portion of the graph here. So now we'll talk about assigning agents to these subgraphs. Basically, the pseudocode here, what it's saying is it's going to iterate over all the vertices in the subgraphs, deciding if an agent occupying a vertex should be assigned to that subgraph. There are two kinds. There are vertexes that only connect, or I'm sorry, there are ones that only connect to vertices in the subgraph, and there are those connected to the vertices outside the subset. Those ones are called joint vertices. So I'll show you in A7 would be considered a join vertice because it's connecting a non-trivial component. This one has a degree of 3 to another non-trivial component. This has a degree of 3. So this would be what we're talking about. Um, in terms of the priorities, um, what the pseudocode does is it essentially checks to see if an agent will be blocked, um, and it assigns priorities to prevent that from happening. So in an instance here where 8 and 9 are trying to move, we would need to set the vertices or the agents at in the subgraph S4 as a higher priority because we have to move these out of the way in order to perform this exchange operation. And if this is locked into place, because if S3 has a higher priority and this can't move, then we have caused a failure by being unable to order this aspect. Um, it's also important to mention that agents that are not assigned to any subgraph, which is possible, they're also not assigned a priority. Um, they'll still be planned, but it'll happen after all of the agents that have priority have already been planned. Next, we're going to talk about the first kind of method for approaching this, or the first operation involved. It's called a push operation. This essentially it tries to move an agent R residing at fancy AR to a new location V. Um, and if V is occupied, then we add the current location of the agent R to a set of locations, which is that fancy U, which agents cannot be moved. And the call clear vertex operation, um, it iterates over all of the empty vertices, and it starts each iteration by finding the shortest path, but also avoiding all of the blocked vertices that are in the set fancy U. Uh, if such a path is found, what will happen is all of the agents along the path move one step towards the empty vertex U or V. No, I'm sorry, U is the empty vertex. Now we'll take a look at the swap operation. This is our heavy hitter. You'll see when we look into our runtime analysis, but swap is really the bulk of our running time here. What it does is it attempts to exchange the locations of two adjacent agents R and S by moving them to a vertex of degree 3 or higher, and then performing the exchange operation there, and then moving everything back to where the swap was initiated. Reverse moves made by uninvolved agents. So, like, if we push anything out of the way on our way back, we have to ensure that it gets moved back. Multi-push, which is described here, is an operation that attempts to move swap candidates to a candidate swap node. So that's where we're pushing it towards the vertice where we're able to um, uh, perform that the clear and then the exchange. Um, and since all of the moves that are not involved with the operation goal will be reversed, we can actually, in this instance, ignore the blocked agents that are in big U or fancy U. We can move them aside because we will be undoing everything except for when we make our exchange. In the case that multi-push does succeed, we now have to call the clear function to make some room for the exchange operation to work. Um, it's just ensuring that we record what was in, if anything, the two vertices extending from, or the other two vertices extending from our degree 3 vertex, um, so that we can make our move and then undo it. Rotate is a new one for push and rotate specifically. Um, what it does is it assumes that there is a cycle of C locations, and it moves all of the agents in that cycle one step. Um, the moves get reversed after the goal is reached, similar to swap. Um, for this one specifically, I found it a lot easier with the visual. So I'll walk through this real quick with you guys. Um, so what we're going to do is we are going to push A1 and AX and AY away from the cycle so that we can open up that degree 3 vertex. Now what we're going to do is we're going to perform our exchange, or we're going to move A2 forward um, to open up this vertex here so that we can push all of the agents that are in the cycle around 1, so that there's enough room here for A1 and A2 to make that swap, like I mentioned. And then what happens is, excuse me, there's another open I'm sorry, there's another open vertex, so we're going to jump all the way around again. We're going to keep moving our agents, and then we're going to push A2 back onto the cycle. So yeah, as you can see, A2 and A1 have switched here, and A1 would now be in its goal configuration. Now, push and rotate, what this does is it determines what the subgraph division is going to be. And then from there, it actually makes the assignment of the agents to those subgraphs, both the initial and the goal assignments, that is. If they're not equal, then the instance isn't feasible and returns false. If that's not the case, we send the parameters to solve operation, and that's where the bulk of this is going to happen. And solve is what is going to transform our initial agent assignments into the goal assignments. Now for this operation, we're trying to move these agents to their destinations one at a time, and we have to do it one step at a time. And we're again trying to do it along the shortest path. So push is always tried first because that's our cheapest. We want push to work as much as we can, because if push fails, swap, like I mentioned, is the most expensive. That is performed. So if push fails, swap will work. And there is a proof in the article about that. It's also important to mention that when an agent reaches its final destination, it is added to a set fancy F, which is all of the finished agents. Its path that it has traversed, it gets recorded in Q. And the finished agents can't be pushed, only swapped or rotated, because they have a higher priority. When moved off of their destination, they are stored in Q and referred to as resolving agents. And when they get returned, they are returned to their title of finished agents. If a resolving agent is moved by a rotate, it actually returns anyway. And that's shown actually in the rotate function. Now, lines 26 to 20 or to 35 here, these bad boys right here, this while loop. Um, what this does is they're used to shrink the queue and make sure that we are returning all of the resolving agents to their final destination, which we move them off of. We have to check for polygons again because if the graph is, then we have to choose a path that avoids finished agents because we can't swap it all in a polygon. The inner loop at line 14, what it does is it moves R towards its destination. Uh, if the next step on the path or R is also on Q, um, then we have detected a cycle of resolving agents, and so we move them all by calling rotate. Uh, otherwise, we attempt to push because again, it is the cheapest. That's shown on line 21. And when that fails, or if that fails, we call swap line 22. When the while loop on line 14 has finished, agent R is added to the fancy F, the set of finished agents. And when we pop back up to start a new iteration of the loop, R is reset to undefined. Uh, now we clean out Q and make sure all the resolving agents have been returned. And if their goal, so while we're going back through Q and we're trying to move a resolving agent back and their goal destination is actually occupied, then we break and we start a new iteration of the while loop at line 14. And we basically now set that agent R as the occupant. So there's a lot of moving pieces, but it is super interesting um, to look at how it works, especially with the visualizations. Um, it is very interesting, and I feel like a good combination between complex and simple. Um, but very interesting algorithm in my opinion. Um, it runs pretty fast. So K refers to the number of agents in the instance, and N refers to the number of vertices in the graph. Each agent needs to be sent to its goal position along the shortest path of length less than or equal to N. And the runtime of the swap operation is dominant. So we'll start here. And I know this is a little goofy, but I'll show you. We start with tsolve, and this is the time complexity that they showed for tsolve, and they went on further to say that tswap, it takes this much time, and multi-push and clear, they both require big O of n times t of clear vertex. So clear vertex requires big O of the absolute value of the vertices plus the absolute value of the edges. And that simplifies down into big O of n squared. So each um, each of these is going to end up being I'm sorry, n times, I'm sorry, T clear vertex takes the big O of V plus E, and that equals big O of n squared. However, multi-push is big O of n times T clear vertex. So multi-push actually ends up giving us a big O of n cubed, which is shown here. So replacing those, we're able to get 2 of n cubed times n, which gives us 2n to the 4, which we'll bring back over here and pop into the tsolve, which ultimately narrows down to what they gave us at big O of k times n to the 5th, which is pretty good. The solution quality, though, is where I find it to be more impressive. It essentially narrows down, as you can see, into big O of k times n cubed. Buy box, which I mentioned earlier, we're going to do some comparing to. It was designed around 2009 by Cernic, uh, an algorithm that we will compare. Oh, yeah, I just said that. But it's actually able to achieve the number of moves in only n cubed, which is um, actually the bound for this problem. And that is defined by, I believe the name was Kroshner, but I had mentioned it earlier in the lecture. I just call this lecture my presentation. um, and again, just a reminder, the quality refers to the number of moves that solves as the output. So now we'll talk about the heuristics and the post-processing of this algorithm. We um, we're trying to remove as many redundant moves as we can, if all of them. Um, that's referring to like if an agent visits a vertex um, for a second time, so it has been moved off and then moved back, and no other agents have visited that vertex in between those moves. That would be considered a redundancy. So we'll scan back over our pi and uh, uh, we'll search for redundancies and we'll remove them, and then we'll update the pointers correctly so that pi is still correct, and then we will check again to see if the removal of that redundancy had actually triggered an additional redundancy. This is all done within the smooth function. Oh man, excuse me. This algorithm actually also uses some parallelism. Uh, every time we step, we look at all the empty vertices, um, and all moves going into an empty vertex are done at the same time step in this instance, and the empty vertices are then afterwards updated accordingly. Um, there is another instance where we are able to move the vertexes behind us in tandem with the one we're moving, because it obviously leaves an empty vertex. Um, Very similar to how rotate works. Um, And I wanted to show that throughout all of these figures I'm going to show you, it's important to note that P and R is our push and rotate. And the no order refers to the fact that they didn't use any of the heuristics for this symbol, but they did use the heuristics for the OG push and rotate. Map is another algorithm that they briefly described in the article. Um, my understanding is it works quite differently and refers more on trees. So I didn't want to cover that one too much. I wanted to focus mainly on um, push and swap, which I said, is what we're built off of here. Um, but it's important to note that push and swap are really similar, like I mentioned, because we built off of it. So we can expect them to behave similarly in these instances. Um, Experiments conducted, uh, not all of them. There's an experiment at the end where they conducted on a non-biconnected graph instance. But BiBox can only work on biconnected graphs, so majority of the experiments are done on those. And we'll actually pull some statistics here shortly, but push and swap is very restricted in what it can do, and it actually fails to solve a lot of the time. For figure 17, uh, this is a comparison done on all of them, um, And as you can see, A and B, respectively, are the number of moves in the CPU times. Um, it's important to note here that as as we uh, uh, the moves all remain relatively the same um, for this instance. However, push and rotate clearly runs faster than its competition. Um, for figure 18 shown here, it's clear that buy box wins for sure. Compared to PNS and PNR, um, the uh, I'm sorry, PNR can actually solve a lot of these problems. PNS only managed to solve 1.17% of the problems presented, in fact, which again shows the shortcomings of PNS and what PNR is able to um, do based on PNS. Next, we'll take a look at the some random instances with handles. And I know I didn't define that term earlier, but it's a buy box term. It refers to how buy box solves it or solves it its way. I didn't find it necessary in understanding PNR, but try to think of it uh, uh, like a flower, like flower petals. Once we have gone through all of the vertexes on the flower petal, we're able to actually disregard that flower petal. Um, that's the best way that I can think to describe it at this time. But um, we give them 40 handles with an initial size of 5 and a maximum handle size of 10. And in this case, we can see that although PNS works really well for these instances, it's still only managed to solve 53.9% of the problems. Um, in as you can see, it was able to do it in less moves um, than the others. Um, but as you can see, also in terms of um, the make span here, um, uh, push and rotate, both with the heuristics and without, it beats buy box in this instance. This table down here refers to the parallelism, um, which is essentially the number of moves divided by the make span. Buy box plus plus is actually just buy box, but it's using push and rotates, smooth and condense functions in the heuristics. Um, so that's why we're able to get better results here for buy box. We use the heuristics involved in PNO. But you can see that buy box plus plus doesn't catch up to our PNR until we have 30 empty vertices. So we will make some more manipulations to the initial cycle and the handle size, as well as the oh no, I'm sorry, it remains 2 empty vertices in this situation. And as you can see, uh, there was a scripting error that resulted in having to cut off PNR's results here, but you can still see the trend. And as you can see, we're able to process these problems with far less make span than the competition here between buy box and buy box plus plus. Push and rotate wins even without the heuristics, it wins. And as you can see, the heuristics involved did make a difference for buy box. Um, but in terms of um, the difference here, we can clearly see that um, when we manipulate the initial cycle size, that's ideal for using PNR. Whereas if we're manipulating the handle size, that's all buy box's thing, um, and is able to do it really fast, especially with the heuristics involved. Um, for this instance, um, push and swap was only able to solve 31.9% of the problems that it was presented. Um, and as you can see, for push and rotate specifically, the heuristics played a huge part uh, in the results here, because push and rotate with the heuristics wins all day, but without it, it clearly it gets up into a higher make span. For figure 22 here, I found it pretty interesting. What we're doing is we're increasing the number of empty vertices for the same 24 by 24 grid. Um, and we're finally into our grid instances here, by the way. This is where we really get to see push and rotate shine. And as we um, increase the number of empty vertices, we obviously have to perform less and less swaps. So it's going to downtrend. Um, and I thought it was interesting how much the heuristics played a role in these aspects as well, regardless of how many vertices there were. Obviously, it got a little closer um, as we move towards having less and less swaps, but the heuristics are insane for this particular algorithm. Um, Lastly, we mess around with the grid sizes. And we also increase the number of empty vertices again. But I found it interesting on how a buy box just absolutely cannot handle doing these kinds of instances, and how well inconsistent push and rotate is able to knock out these solutions, especially with its heuristics. But lastly, I just wanted to mention and say that push and rotate is a complete and polynomial time algorithm that solves the multi-agent pathfinding problem. Um, it can be improved upon. It is the problem is by no way finished. We have more work to do here. Um, it doesn't achieve the best possible worst case bound, which is defined in the article as big O of n cubed moves. Um, but it is able to provide or produce competitive results, especially compared to buy box and especially push and swap. Um, and it's important to mention that it's able to be competitive while buy box actually does meet that bound. Um, but another important aspect about this algorithm is it's not limited to specific graphs like buy box is. Um, but the push and rotate, especially with the heuristics, is definitely arguable to be the algorithm of choice. So uh, I'll show my works cited here for a second, and thank you all again for tuning in. I hope you were able to understand what I was trying to explain. A lot of moving pieces to this algorithm, so I apologize if something didn't make sense. But yeah, that's multi-agent pathfinding, push and rotate method. Thank you so much.